Hi 242. So this is the video for the second part of section 13.4 where we're going to discuss what's called the definite integral. So we've already defined the definite integral together because you already did a little bit of reading from section 13.4, but now we can actually do our little video together so that we can walk through a couple of examples. So the first thing we should talk about is the notation, right? Just to refresh ourselves on what this notation actually means. So remember last time when we were discussing sort of finding areas underneath curves, remember that we were able to come up with an exact way of figuring out areas underneath curves. And we did this crazy adding up rectangle stuff, and then we said, wait, let's use infinitely many rectangles under a limit, right? And somehow it miraculously turned into this notation here, right? Which, remember, this notation for this definite integral represents the true area underneath the curve. So remember, this equals area under f of x from x equals a to x equals b. And so if you're thinking about that graphically, right, if you had some kind of a graph of f of x here, right, and you said you were going to go from a to b here, then the definite integral right here is representing all of this area underneath here, right? All of that stuff. That's what this definite integral is representing. And remember that we said that number right there, that area, is the result of applying a limiting process to a sum, right? And if you have to see the fancy notation for that, remember it was something like this where we had the limit as n goes to infinity, and then we had like a summation thing here, and we had f of x, xi, I delta x, and I went from 1 to n. Okay, and we had to have all of these different parts here, right, to say this is the addition of the area of a bunch of rectangles, right, because this is height times width, right, so that's an area of a rectangle, and then we add up all of the rectangles areas, and then what we do is we say, well, we've decided we're going to use lots and lots of rectangles, meaning let the number of rectangles here that we're indexing here, let the number of rectangles go to infinity. Okay, and under that limiting process, this summation here, this sum, this Riemann sum, remember we use that word Riemann sum, actually turns into the true area underneath the curve of f, right, from A to B. Okay, so this is better notation, right? And we'll see in the next section in 13.5 why this notation is actually really useful. But for right now, for all it means for us right now is geometrically the area underneath f of x from x equals a to b. There's a couple of words that we should talk about in terms of terminology, right, that we already know. Of course, we know this thing right here, that's called the integral sign. We already know f of x, that thing's called the integrand. Right? But now we have these numbers, these a and b, right? That's telling us where to start and where to stop accumulating area at. And so these are what are called the limits of integration. And of course, since there's one on top and one on bottom, we have to make a distinction between them. This is the upper limit of integration. And correspondingly, then a would be the lower, right? Lower limit of integration. Okay, I'll let you rewrite all of that stuff, but A is the lower limit of integration. Okay, so now that we have this definition sort of sorted out for ourselves, right, and we know that geometrically this is the area underneath a curve here, maybe we should go ahead and try an example problem where we make use of this notation to say I'm calculating the area underneath a curve. Okay. So one last bit of reminding here is that last time in class we sort of determined that there has to be some sort of a distinction between area that happens above the x-axis and area that happens below, right? So for example, if you notice over here, I have the graph of a function f of x, and part of the graph goes above, part below, and then part above again, right? So if you were to imagine, it's trying to approximate this area with our rectangle business that we've done before, right? The area here, this green stuff here, would be approximated by areas by rectangles that are above the x-axis, right? Their heights would be positive, right? The heights of those rectangles would be positive. Okay, so this area right here in green would be approximated by a positive number. because the heights are all positive. This area in yellow here, if we were to approximate it with some rectangles, the heights of those rectangles would be negative, right? Because you go down to calculate the y value in order to get a height of a rectangle. So because of this, what we've decided is that area which happens above the x-axis is considered positive, and area that happens below is considered negative. And so it's beneficial to make that note to yourself, right? So area above x-axis is positive, right? And area below x-axis is negative, right? And so that'll help us now when we work through this example when I start writing definite integrals. So let's actually calculate some areas underneath the curve. So let's say, for example, that I wanted to calculate the definite integral. Let's see, the function I want to work with is this f of x graph over here. It doesn't have an equation or anything, but I'm just going to call it f of x. Let's go from a to b. Right? And again, we don't have numbers for a and b. Usually there would be numbers like 0 and 1 or something, right? But for right now, we just are dealing with letters. Okay, so this, remember, says what? This is asking for the area under f from x equals a to x equals b, right? Okay, well, let's see. That would be all this green stuff. Do we know the area of the green stuff? Well, luckily, we're told, right? Okay, this is harder if we're not told, okay? Because again, notice this isn't like a semicircle or a rectangle or any nice shape, okay? If it's not a nice shape, we have a little trouble figuring it out. But for us, we're told that that green area is 2, so I can just write 2. It gets a little bit more tricky if I then say I want to go from A to C. Yeah, because now I want the area under the curve. Again, remember, under the curve means trapped between the curve and the x-axis. Going from A to C now says you want to do green and the yellow, right? You want green and yellow. And remember that word and means that I want to combine the two things. But remember, area above is considered positive, so we already know that green stuff is 2. Right? But how do we consider the yellow stuff? It lives below the x-axis, which means it's negative, right? So you could write this as take the green stuff, 2, and then add what? The area of the yellow, which is considered negative, and what's the area of the yellow? It says 4. Okay. Now, why did they not write negative 4 right here? That's because they're just telling you what the actual area is. It's up to you to decide whether it should be positive or negative. We decide negative because it lives below the x-axis. Okay. So that means this is really 2 minus 4, which is negative 2. And you're probably asking yourself, wait. An area is negative, right? Well, we just said it was over here, right? The yellow area. But this kind of makes sense because notice that it says the area for under the curve from A to C is the total of the green and the yellow. Well, is there more stuff above or more below? If you notice, the yellow is a little bigger than the green, right? Which means that there's a little more negative stuff than there is positive stuff. So our final answer should be a negative number. Okay, let's finish this off by going from A to D. Let's see what we get. Okay, going from A to D, I want everything. I want green plus yellow plus pink, right? So green is considered positive. Its value is 2. I add to that the area that's yellow here, but that's negative, so it's below the x-axis. So add a negative, whatever the number is, 4. And then I add, again, this pink stuff happens above the x-axis, so it should be considered positive area. What is its area? Its area is 1, so I add 1. Okay, so this is what? 2 minus 4 is negative 2, plus 1 is negative 1. Okay, and it's still negative because why? Well, because if you look at the green and the pink together, they are still not more than the yellow stuff, right? So there's that yellow stuff is really sort of taking control of this situation here. Okay, so that's how we can make use of what your book likes to call signed areas, right? They use this word signed areas. Okay, all that means is you have applied a sign to some kind of areas. You've considered some positive and some negative, others positive again, right? And we have been able to use this notation for the definite integral. All right, so let's check out some properties of the definite integral. Some are inherited from properties of a indefinite integral, but others are just specifically geometric, right? So these are properties of definite integral. And if you'd like to follow along, there is the properties on page 737. Okay, and so the first of these properties is something that looks like this. let's see if we can think about what this should equal. This says to do what? Calculate the area under the curve starting at A and going to A, right? If you were to think about that sort of with a picture for a second, right, that would be something like you had F here and you start at A and you go to A. Did you trap any area underneath the curve? Did you even move your x value over to start calculating area? No, you did not. Okay, so what that means is we didn't accumulate any area. So that definite integral right there has to be 0 because you didn't go anywhere, right? You started at A, stopped at A, you didn't accumulate any area. Okay, so anytime the limits of integration match, the integral is always 0. All right. Second property is something that you've seen before with indefinite integrals. If we have a constant living in front of the integrand here, well, then it says that the constant can just come out front. Okay, so that's not too surprising because we've done that before with our indefinite integrals. Constants can just come right out front. That's good. Something else that is similar to our indefinite integrals, our antiderivative notation we did before, is that sum or differences can also be handled individually by the definite integral here. So if you had the sum of two expressions of x inside an integral here, if this was the integrand where you added two terms or something, then what this means is that the definite integral can just apply to each of the expressions of x, plus or minus a, b, g of x. Okay, great. Let's see, there's two more. So let's get number 4 here. Okay, this one will just use a bit of a geometric argument here. So if we go from A to B, right, notice that, remember geometrically, that means doing something like this, right? Here's F, and I go from A to B, right? Well, this property says that if you want to, instead what you could do is say, well, I could think about this in terms of like pieces, right? And I could say that there's like some C in between here, and the area underneath the curve here from A to B, that shaded in stuff, let me shade it in black so you see what I'm shading here, that right there, all of that stuff there is equal to, say, doing this part right here plus this part right here. Right, so just thinking about it in two pieces like that, and you're like, why would I even bother ever doing that? Well, it might be useful later. It's a good property to have. So this says that we can do what? The area from under the curve of f from A to C, and I can add to that the area from C to B. Okay, good. So that's sort of like putting the pieces together, right, to get the whole thing. That's what that one's all about. Okay, so let's make use of that for a second to notice something here, to get the last property. So if I write this, right, we know that this is 0, right? Okay, but I can make use of property 4 here to rewrite what happens on the left side here. If I wanted to be sneaky about this and just sort of blindly apply property 4 here, I could say that I could go from A to some B, right? And then I could go from some b to the upper limit of integration for this one, this a right here, which is just a again, right, of f of x, right? So notice this is using property 4. If I go from A to something, right, it doesn't matter if they're whatever the letters are, I can go from A to something and that same something to the upper limit, right? As long as the lower and upper limits are the same here, I can insert whatever I want at the upper and lower here and the integral is still true, right? If I go from A to B, then insert a C here, and it's just important you go from A to B, right? And that's the same thing I'm doing here. I want to go from A to A, so I'm going from A to A, but I insert a B however I want, right? Okay, it could have been the letter C, it doesn't matter. Okay, but I know that this is still equal to 0 because I know this stuff on the left-hand side is A to A. Okay, but what's interesting is that when see what happens when I move one of these integrals over to the other side. Okay, so what this says is that if I go from A to B, right, that's this left integral here, that's equal to, move this one over, negative integral B to A. Aha! This is the property itself. What this says is that if you want to switch the limits of integration, if you go from a to b, you can instead go from b to a by just throwing a negative sign out front, right? So again, you can reverse the limits of integration is what this really allows you to do, as long as you throw a negative sign out front. Okay, so reverse the limits of integration, put a negative out front. All right, so let's finish this video of 13.4 by finishing off with an example. And I'm going to be doing one from your textbook. So this is going to be matched problem 4, E. Okay, so in this problem, we're given some information. We know the value of some definite integrals. We know this one's 2. We know this one is 8/3. And we know 2 to 3 of x squared is 19/3. Okay, this is stuff that we're given. We know all this stuff. This is given to us in the problem, right, in example 4. Okay, so what we're asked to do is to find this integral, 0 to 3 of 12x squared dx. Okay, we're asked to find this here if we are given all of this other information up here about these 3 definite integrals. So let's make use of our properties of the definite integral to see if we can break this thing apart. Because notice I don't know what the value of the integral of 12x squared is from 0 to 3. That's not one of the ones I know anything about. I know the integral of x squared from 0 to 2 and x squared from 2 to 3. So maybe we can like piece this together. Okay, so let's first start rewriting. Notice here that that 12 out front here, right, is a constant. So one of our properties says that if there's a constant living in front of the integrand, that constant can come out. So I can write this as 12 integral 0 to 3 x squared dx. Okay, what else can I do? Well, I don't know what the value of the integral of x squared from 0 to 3 is. I only know, let's see, what do I know? I know x squared from 0 to 2 and x squared from 2 to 3. But remember that one of our properties here says that if I know 0 to 2 and 2 to 3, then I can say that something about that is from 0 to 3, right? So let's see, this is 12 times whatever this whole thing is, right? So I'm going to write 12 times 0 to 2 x squared dx plus 2 to 3 x squared dx, okay? And that's making use of that additive property where if I go from A to B and B to C, that's the same thing as going from A to C, right? 0 to 2, 2 to 3 is the same as going 0 to 3. But notice I actually do know values of these 2 definite integrals, right? So this is 12 times, let's see, 0 to 2x squared is 8/3. We're told that. And then I add to that, what is 2 to 3 of x squared? 2 to 3 x squared is 19/3. Aha. Great. So now I can actually just add these two things, right? 8 and 19 is 27/3, which is 9 times 12. So 12 times 9, okay? Which is, let me guess, 108. I'll let you determine if that's the correct number or not. Okay, so that's how we can make use of these properties of the definite integral here to calculate values. Notice we had to be given a bunch of this information. In the next section, we're actually going to figure out how to find specifically these things without being told them, right? It's a really important theorem. But for right now, that's good.